Sometimes, like this problem, we have a more complicated geometry. For example, in this problem, B37, we have this rod with the mass of m with this shape in 3D, and we want to find what is the mass moment of inertia about x, y, and z axis. So how we can solve this type of problems? For this type of complicated problem, complicated geometries in general, you should split the part in smaller parts that we know we have some information about the mass moment of inertia of them. For example, for this one, I'm gonna call this part 1, and this part at the middle 2, and this part at the bottom 3. And we can find the mass moment of inertia of each of them separately about any axis and then add them together. We call this geometry is composite geometry, so composite parts. So for example, let's start with probably the simplest one is the y-axis. What is I of the whole object about y-axis? So starting with the first one. First of all, what is the mass? The total mass is m, so the mass for the first part is going to be m over 4, and for the second part the mass is m over 2, and the last piece m over 4 again. Now, what is the mass moment of inertia of the first one about the y-axis? We have solved this problem before. We know whenever we have a rod, the mass moment of inertia about the axis which is passing through one end of it and perpendicular to the rod is going to be 1/3 of mass times length squared. So the mass moment of inertia for the first part is going to be 1/3 of its mass, which is m over 4, times length squared, b squared. What is the mass moment of inertia of this rod about y-axis? The second one. If you remember the mass moment of inertia of a cylinder about its axis, it was 1/2 of its mass times radius squared. But the radius here is very, very tiny. It says the diameter of the rod is negligible comparing to the length of it. So the mass moment of inertia of this part is going to be 1/2 of its mass times very small radius squared, which is going to be even smaller. So it is 0. We can say it is 0. Comparing to this part, and also for this one, it's going to be negligible. So for the second part, it's 0. And for the last part, it is similar to the first one. We have a rod perpendicular to the y-axis, and y-axis is passing through one end of it. So the mass moment of inertia is going to be 1/3 of its mass, which is m over 4, times length squared, b squared. So if you add all of them together, it's going to be 3/4 of the mass times b squared. For z-axis, so let's do the z-axis. So what is the mass moment of inertia of the first part about the z-axis? We can solve this in different ways. One way is using parallel axis theorem. What's the meaning of that? Look at this axis, which is passing through the centroid of the first part, right? And it's parallel to the z-axis. The mass moment of inertia of the first part about z-axis is going to be equal to, based on parallel axis theorem, it is equal to the mass moment of inertia about this axis plus mass times distance squared. Now, what is the mass moment of inertia about this axis? Similar reason, it is equal to 0 because the diameter of this bar is tiny. So it's going to be, the remaining is going to be its mass times distance squared. Its mass is m over 4, and the distance is b. Second part, what is the mass moment of inertia of this one about the z-axis? And if you remember, we had similar problem. This was the first problem actually we solved in this part. The mass moment of inertia of a bar about an axis which is perpendicular to it and is going through the centroid of it is 1 over 12 mass times length squared. So it's going to be 1 over 12, its mass, which is m over 2, times length squared, and the length is 2b here. And the last one, how about this one? What is the mass moment of inertia of this one about the z-axis? Again, you can solve this using different techniques, but probably one easy way is this, using parallel axis theorem. If you want to use parallel axis theorem, you need to find the mass moment of inertia about an axis which is passing through the centroid of your part and is parallel to your target axis, which is z here. So I need to find the mass moment of inertia about this axis, then add mass times the distance squared, the distance between these two axes, right? Which is this. Now, what is the mass moment of inertia of the third part about this axis? Same way, 1 over 12 times mass, which is 1 over 4, times length squared, which is b, plus mass times distance squared. Mass is m over 4 times distance squared. What is this squared? It's going to be b squared plus b over 2 squared, right? So the distance squared is b squared plus b over 2 squared. So these two together is the mass moment of inertia of this part, the third part, about the z-axis. If you do the math, add all of them together, it's going to be 3/4 of mass times b squared. How about the z-axis? Again, similar thing. Sorry, x-axis. For this part, we need to find the mass moment of inertia about this axis, then add mass times distance squared. For this part, 1 over 12, it's mass times the length squared. For this part, it's going to be this mass times the distance squared, right? So if you do all that again, I guess I made a mistake here. Iyy, it's 1 over 6 times mb squared. I misread it from my notes. So ixx is going to be similar to izz, right? We have everything similar to here. So at the end, you are going to get 3/4 of mb squared.